we are going to discuss about energy method. This is another type of method to find the deflection, in beams. Uh, as far as Maxwells method is concerned, it can be used for cantilever beam, uh, simply separated beam, overhanging beam, for different kinds of problem. But however, there are some limitations in this problem that cannot be used for some different types of beams. So now we are going to discuss about the energy method. So by knowing the energy method, different kinds of beams can be deflection of different kinds of beams can be solved. So now already we have discussed about uh, strain energy stored and work done, isn't it? In case of a member, say it's an axial member, a beam, a structure subjected to axial load. Then what is a, let us take this is W. Then what is the work done? Equation for work done, that is equal to, say this is deflection is equal to delta. Then work done is equal to half into W into del. This is a work done. Then what is the equation for strain energy? Strain energy stored when work is done, that will be stored in the form of strain energy. That is given by sigma square by 2E into volume. Whatever work we give, that will be stored in the form of strain energy. Now, if it is a torsion, then how to calculate the work done and strain energy? So this is a shaft subjected to a torsion. Angular twist is theta. Then what is the work done? Work done is equal to half into T into theta. This is the work done. What is the amount of energy stored? Strain energy stored. That is, here what is the stress? Stress is tau. So tau square divided by 4G into volume. So this is the equation we have seen. This is the work done in case of a shaft subjected to torsion. This is the strain energy stored. Here G is the modulus of rigidity, tau is a shear stress. This is in case of axial. But we have not discussed about beams. In case of beams, how to find the strain energy stored? That we have not discussed. So that's what we are going to discuss now. Now, in case of a beam, you assume that deflection is equal to del. Then strain and work done is equal to half into P into del. P is a force applied. Otherwise, you can say W. Here also, half into W into del. Am I right? So this is the work done in beam. So this is a load W. And the deflection. It is subject to a deflection. The deflection is equal to how much? It is delta. Then work done is equal to half into W into del. Then what is the amount of energy stored? Strain energy stored. So to calculate the strain energy stored, we have a equation. The length of the beam is L. Then integrate within the limit 0 to L, m square. What is m square? M is equal to moment. You got to write the moment in terms of x. 2 into E is equal to young's modulus, I is equal to moment of inertia into dx. So by using this equation, you can find the energy stored. So now, for a cantilever beam, we are going to calculate the strain energy stored and work done. So from the equation work done and strain energy stored, we can calculate the value of delta. We can calculate the value of delta. So for a cantilever beam, what is the value of delta when it is subjected to load at free end? When it is subjected to load at free end, what is the value of delta? You may be remembering that is W into L divided by 3EI. So this is the value of delta. Already we have done. Already we have done derivation using the double integration method. By using the double integration method, we did. However, we are going to calculate the deflection by using the energy method also. In the energy method, we are going to compare the work done and energy stored. So what is the equation? Now I am taking an axis here. Now I am taking an axis x. Now I am taking x. So I am taking this. This is origin. I am taking this is origin. From here I am taking a distance of x. I am taking distance. Then about the axis, what is the value of moment? Moment is equal to what? Load into distance. So W into x. This is a moment. Now, what is the equation to calculate the strain energy stored? That is U is equal to integral. What is the length of the beam? 0 to L. 0 to L. It is varying from 0 to L. Length of the beam. That is a limit. M square. What is moment? Moment is equal to W into X. So M square. That is W square X square. Right? Divided by 2 into EI. 2 into EI into dx. Right? Into dx. So now you integrate it. And take the constants out. What are all the constants? W square is constant, 2 is constant, EA is constant. You take outside. W square divided by 2EA integral x square into dx. So now W square divided by 2EI. If you integrate x square, what will be the x cube divided by 3? What is the limit? 0 to L. 0 to L. Now apply the limits. W by 2EI into L cube by 3. L cube by 3. If you put 0, that will be 0. So if you substitute the limit L cube by 3. What is this? This is the strain energy stored. This is strain. That will be equal to what? That will be equal to work done. What is the work done? Half into W into del. Now half you cancel. Sorry, W cancel. 2 you cancel. Now what is the value of delta? Delta is equal to. So this is W square. So this is W square. Square will be cancelled. W if you then the equation is, what is the equation? Delta W L cube divided by 3EI. So this is the value of delta. Already we know this equation. We have derived this equation by double integration method. However, by energy method also we have derived this equation. Now we are going to see one problem. Now you see this problem. In this problem, determine the deflection under 60 kilonewton load. You need to find 60 kilonewton load under this load, as shown in the figure. Now, here the beam is not having uniform cross section. Up to this, one cross section. After that, another cross section. There are two cross sections. These type of problems cannot be solved by a double integration method, because EA value is changing. So for this, energy method will be suitable. Now what we are going to do is, we are dividing this into two. We are dividing this beam into two beams. This is beam 1, this is beam 2, right? I am going to calculate the energy stored by beam 1 and beam 2. Both are same beam only, but our calculation purpose, we are dividing into two sections. Section 1 and section 2, right? The section 1 distance is 4, section 2 distance is 4. I am calculating the U1 plus U2. U1 plus U2. What is U1? Energy stored by the beam by section 1, and energy stored by section 2. Right. To calculate section 1, I am taking an axis here. I am taking axis here. This is for the section 1. I am taking this is origin. This is origin, and I am taking this distance as x. This is a x. It is varying from 0 to 4. 0 to 4. This distance is 4. Similarly, for this, I am taking an axis here. I am taking an axis here. I am taking this is x. This is x. This is origin. It is varying 0. It is varying from 0 to 4. 0 to 4. Right? Now, what is the value of RA? What is the value of RA? Here, total load is 60. Total load is 60. It is exactly acting at the center. It is exactly acting as the center. So, this will be 60 by 2, 30. This also 60 by 2, 30. Right? Now, U1. U1 means I am taking about this axis. I am considering the left side. I am writing a equation. What will be the equation? I'm U1. For that, what is the equation for energy stored? Integral m square 0 to L. M square divided by 2 EI into dx. This is the equation. M square. So here 30 into x. If you take moment about this point, it is 30 into x. So 30 square into x square. M square divided by 2 EI. 2 EI plus into dx plus what is the limit? 0 to 4. The length of the section 1 is 0 to 4. Similarly for 2. For this also distance is from 0 to 4. 0 to 4. Here also 30. So here also 30. 30 square x square divided by 2 EI. 2 EI. Here the EI value is EI only. But here EI is equal to 2 EI. EI is equal to 2 EI. The size of the beam is little bigger. So 2 into EI is how much here? 2 EI. 2 EI into dx. So now we have to integrate, apply the limit. You will get the total energy stored in the beam. That is equal to, let us take here commonly outside, 30 squared by 2 EI, right? Here 4 EI. Let us take like this. 30 square divided by 2 EI plus 30 square divided by 4 EI. Here 0 to 4, same limit, x square into dx. Can we write like this? Yes. We have taken commonly outside what? Integral x square dx. We have taken commonly outside. So within the bracket, you will get 30 square by 2 EI, 30 square by 4 EI. Now if you take 2 EI commonly, this is 4, this is 2. Let us take 4. Then 4 means it is 2 into 4 EI. Let us take commonly 4 EI. So it is 2 into 30 square plus 30 square. Right? Integral 0 to 4 x square into dx. Here it is 2 plus 1, 3. Okay. So 3 into 30 square. 3 into 30 square divided by 4 EI. 4 EI. If you integrate x square, that is x cube by 3. X cube by 3. Apply the limit 0 to 4. Apply the limit 0 to 4. Then 3 into 30 square divided by 4 EI into apply the limit 4. 4 power cube. 4 power cube divided by 3. Right? If we cancel this 4 and then it is 4 square. 4 square. 3 we can cancel. 3 we can cancel. So this will be 30 square into 16. divided by EI. This is strain energy stored. This is strain energy stored. That is equal to what? Half into W. Half into W into del. What is the value of W? W is equal to 60. Half into W into del. What is the value of W? Half into W is equal to, the load is 60. 60 into del. When, if you get this, if you cancel, this is, if you, this is 2 into 30. 2 into 30. This 2 you can cancel. This 30 you can cancel. Then what is the value of delta? Delta is equal to 30 into 16 divided by EI. Right? That is equal to how much? That is equal to how much? 30 in, it is 480. It is 480. That is equal to 480 divided by EI. This is the value of delta. This is the value of delta. So this is a way you can solve this problem. This kind of problem cannot be solved by Maxwell's method or double integration method. Now let us see another problem. Let us see another problem. Now you see this problem. This problem is something different. Something different. Previous problem also there is a small difference. That is, the beam was having two different EI values. Cross section were different. But here it is like a L shape. It is like a L shape. This also can be solved by energy method. This also can be solved by energy method. Here, if you apply the load, you have to divide into two beams. In the previous problem also, we divided the beam into two sections. Two sections. Here also, we are going to divide this into two sections. So, BC is one section, AB is another section. AB is another section. So now, then what are all the load acting on the AB? That also you have to calculate. Because of this load, how much amount of load will be acting at AB? That you have to see. This 1 kilonewton load. Now I am transferring the load here. I am taking here. Here this is 1 kilonewton. This also 1 kilonewton. Equivalent opposite force. Equivalent opposite force. So now this and this will create a couple. Equivalent opposite force separated by distance. What will be that value? This is 3. This distance is 3. This is 4. This is 4. Then now this is 3. This is 4. This is 4. Now the 1 kilonewton load separated by a distance of 3 meters. 3 meters. Then what is the value of moment? Moment is equal to 1 into 3. That is 3 kilonewton meter. What is the direction? This will create a clockwise. This will create a clockwise moment. So now, if you divide this into two beams, one beam will be like this. One beam will be like this. The distance is 3 meters. The distance is 3 meters. Here we are applying a load. Here we are applying a load. Distance is equal to 3 meters. This is one beam. Another beam is like this. Here it is fixed. The distance is 4 meters. And here there is an axial load as well as there is a couple. What is axial load is 1 kilonewton. Couple is equal to 3 kilonewton meter. 3 kilonewton meter. Now energy stored by this beam and this beam you calculate separately, add together. That will be the strain, total strain energy. Let us take this is beam 1, this is beam 2. Now the total energy is equal to U1 plus U2. U1 plus U2. What is U1? Integral. This is U1. What is the distance? 0 to 3. 0 to 3. What is, if you take the axis here, and if you take this is X, and the load is equal to 1 kilonewton. 1 kilonewton. 1 kilonewton. Then M square. What is the value of M? 1 into X. So X. M square is equal to X square. Moment is equal to X because load is equal to 1, distance is equal to X, 1X. X square, M square divided by 2 EI. 2 EI into dx. This is a strain energy equation for beam 1. So now you take for beam 2. Beam 2 plus integral, what is the distance? It is 0 to 4. Distance is equal to 4 meters. So 0 to 4. What is the moment? Here one is axial load. Axial load will not create any moment. Axial load will not create any moment. So you need not take this load. Then the moment. Moment already it is directly moment is given. So 3. 3 square. M square. 3 square. Divided by 2 EI into dx. Into dx. Now you can take commonly outside. What you are going to take commonly outside? 1 by 2 EI. Right? 1 by 2 EI. X cube by 3. X cube by 3. It is 0 to 3. Plus here what is a 3 square divided by 2 EI. We can take commonly outside. Here we have then we have a constant. We have a constant. So what is the integration? X. What is the limit? 0 to 4. 0 to 4. That is 1 by 2 EI x cube into 3 power cube divided by 3 plus 3 square divided by 2EI multiplied by 4. Multiplied by 4. Now if you cancel this 3, if you cancel this will be 2. And then the equation is, what is the equation? 3 square 9. 9 by EI. 9 by 2 EI. 9 by 2 EI. Plus, that let us be 2. This is 3 square. 3 square means 9. 9 into 4, 36. 36 divided by 2 EI. 2 EI. If you add both, 36 plus 9, 45. 45 by 2 EI. 2 EI. That is equal to, this is a total energy stored in the two section. That is equal to half into W into del. W into del. What is this? This is a work done. Here what is W? W is equal to 1. What is W? Here only we are applying the load. W is equal to 1. So here it may be deflecting like this. It may be deflecting like this. So this is delta. This is delta. Half into W into delta. W is equal to 1. Then if you cancel this half, then what is the value of the delta? Delta is equal to 45 EI. 45 EI. This is the value of delta. This is the value of delta. So this is a way you have to solve this problem. Right? Now we are going to see one more problem. We are going to see one more problem. Now you take this problem. This is another problem. This is another problem. So in this problem, here you can divide into 3 beams. Here it is fixed. Here it is a roller. Here it is a roller. When you apply the load here, 5 kilonewton here, this can move like this. This will move. Let us take, this is delta. This is delta. Applied load is 5 kilonewton. Applied load is 5 kilonewton. That's then what is the work done? Half into W into del. Half into what is the W? 5. 5 into del. So that is the work done. So now we have to calculate the energy stored. You have to calculate the energy stored. Now you have to divide into 3 beams. You have to divide into 3 beams. Beam 1, beam 2, beam 3. So each beam, what is the amount of load is acting? What is the amount of load is acting? When 5 kilonewton is acting here, what is the load? I will be acting in each load. You have to calculate, right? This distance, this beam is 4 meter. Then this is also 4 meter. This is also 4 meter. This is equal to 3. This is equal to 3. So this also, this is 3 meters. So these are all the dimensions. This is 4 meter. This is 4 meter. This is 3 meter. The beam 1, 2 and 3. 1, 2, 3. So now 5 kilonewton is acting. This 5 kilonewton. Now what you have to do to transfer here? You take here one 5 kilonewton. Here one 5 kilonewton. So now this load and this load will create a couple. So what will be the direction of the couple? This will be the direction of the couple. Direction of the couple. So here if you see the 5 kilonewton load and this couple you liked. Couple. So same thing you can transfer here. Same thing you can transfer here. The same couple also will be acting here. Same couple also. What is the amount of the couple? That is 5 into 4. 5 into 4. That is 20 kilonewton meter. 20 kilonewton meter. Similarly, here also the same 20 kilonewton will act. Addition to that, there is a load. Here we have a load. The same load will be acting here. Same load will be acting here. So that is 5 kilonewton. So now I am going to draw into 3 beams. I am going to draw into 3 beams. The first beam. This is a first beam, right? About this point, 5 kilonewton is acting. 5 kilonewton is acting. The distance is equal to 4 meters. Distance is equal to 4 meters. And another beam. So this beam. In this beam, what is the load acting here? About this point. A 20 kilonewton is acting. 20 kilonewton meter. Addition to that, there is axial load. 5 kilonewton. This is another beam. Now let us see the third beam. About the third beam, here same 20 kilonewton is acting. 20 kilonewton is a counterclockwise. Then there is a force. This is 5 kilonewton. What is the distance? This is 3 meters. This is 3 meters. This is 4 meters. Now, what is the work done? Work done is equal to half into W into del. Half into, what is the W? 5 kilonewton. 5 kilonewton into del. So this is a work done. What is the energy stored? We are divided into 3 beams. That is total U is equal to U1 plus U2 plus U3. What is U1? As far as U1 is concerned, you take axis here. You take this is X. Then what is the moment? 5 into X. Integral, what is the distance of the beam? 4 meters. So 0 to 4. Moment is equal to 5x square. 5x. So 5 square x square divided by 2EI into dx. This is U1. What is U2? Integral, distance is 3 meters. 0 to 3. And moment is 20 kilonewton meter. Directly moment is given. So 20 square. Moment square 20 square divided by 2EI into dx plus the third beam. Integral 0 to 4. Distance is 4 meters. Here this also will create a here all counterclockwise moment you have taken positive. So this will create a counterclockwise moment that is positive. So 20 minus this 5 kilonewton load will create a, if you take this is x, if you take this is x, that is 5x. So 20 minus 5x. This is a moment. This 5 kilonewton load will create a clockwise moment. Already 20 kilonewton is counterclockwise. So I am taking 20 kilonewton counterclockwise is positive. So 20 minus 5x, that this is m square divided by 2EI into dx. Now we can find the value. That 20, this is a minus b the whole square. How you can write this? That is, we can write this 20 square plus 5x square. So 25x square minus 2 into AB. So 20 into 5 is 100. 100 into 2, 200. 200x. 200. 2AB minus 2AB. This is a equation. If you expand this, you will get this. So now you find the values. This is equal to 25 divided by 2EI within bracket x cube by 3, x cube by 3, limit is 0 to 4, 0 to 4 plus 20 square divided by 2ei within bracket. Here we have only one constant, that is x, integral 0 to 3, 0 to 3 plus here 20x square. So 20 square divided by 2ei, 20 square divided by 2ei into x 0 to 4 plus 25 x square, 25 by 2ei into x cube by 3, x cube by 3, 0 to 4, 0 to minus 200 divided by 2ei. Within bracket we have x, x square by 2, x square by 2, 0 to 4. So this is a equation. This is a equation. If you solve this, you will get 1133, 1133. That is equal to 1133.3 divided by ei, divided by ei. That is equal to half into 5 into delta. From this you can find the value of delta. From this you can find the value of delta. Delta is equal to how much you are getting? Delta is equal to, you are getting 453.3 divided by ei, divided by ei. This is a value of delta. This is a value of delta. So this is about strain energy method. This is about strain energy method. So now we are going to see about moment area method. We are going to see moment area method. It is very simple method. So already we know for cantilever beam. For cantilever beam, what is the value of delta? You know the equation. What is the value of theta? The maximum slope will occur at this point. And what is the value of theta? Theta is equal to W L square by 2EI. 2EI. And delta is equal to W L cube by 3EI. 3EI. Right? This we are going to calculate by moment area method. This we are going to calculate by moment area method. So in the case of moment area method, so this is a beam, cantilever beam. Load is acting at the free end. Then this will be the moment diagram. This will be the moment diagram. Here it will be 0. Moment will be 0. At this point, what will be the moment? W into L. W into L. So W into L. So it will be like a triangle. It will be like a triangle. So what is this? This is a moment diagram for this beam. Right? Now, to calculate theta, the equation is area divided by EI. Area divided by EI. What is area? Area of this moment diagram. Area of moment diagram. Area of moment diagram. What is A? Area of moment diagram. Area of moment diagram divided by EI. So then what is the area? Area is equal to, this is a triangle. This is a triangle. So half into, this is, what is this distance? L. L into W into L. Then what is the value of W? L square by 2EI. 2EI divided by EI. Divided by EI. So this is the value of slope theta. So to find theta, what you have to do? Area divided by EI. What area? Area of the moment diagram. Area of the moment diagram. So half into L into W divided by EI. That is WL square by EI. So this equation we have calculated by W integration method already. WL square by 2EI. Similarly, delta is equal to WL cube by 3I. This can be obtained by, what is delta? Area into X bar divided by EI. Area into X bar divided by EI. What is X bar? X bar means we want to calculate delta at this point. We want to calculate delta at this point. So this is a triangle. This is a triangle. Center of gravity will be here. Center of gravity will be here. What is this distance from this? What is this? What is the distance? This is 1 by 3 L. So what is this distance? This distance is equal to 2L by 3. This is 2L by 3. This is equal to 2L by 3. So we are calculating from this point. We are calculating delta at this point. So you have to take 2L by 3. So here, what is the area? Area is equal to half into L into W into L. This is W into L. This is area multiplied by what? X bar. That is 2L by 3. 2L by 3 divided by EI. Divided by EI. So what is the value of this? If you calculate 2 and if you cancel 2 and 2, then W L cube by 3EI. W L cube by 3. This is the value of delta. So why I explained this is, this method also you must know. This method also you must know. This is known as moment area method. This is known as moment area method. But that Maxwells method and strain energy method itself sufficient to solve any kind of problem. So just to understanding purpose only, I have explained this. This is known as moment area method of calculating slope and deflection. Now we are going to see what is that is Maxwell's law. Maxwell's law. According to Maxwell's law, this is a simply supported beam. This is a simply supported beam. You take a point A and B. There are 2 points. First you apply the load at A. First you apply the load at A and find the deflection at first you apply the load at B and find the deflection at A. Find the deflection at A. Now you apply the load at B. Apply load at A instead of applying load at B. You apply the load at A and find the deflection at B. There are 2 points A and B. First apply the load at A and find the deflection at. First you apply the load at B, find the deflection at A. Now you apply the load at A, find the deflection at B. The deflection at A will be equal to deflection at B. So this is a Maxwell's law. This is a Maxwell's law. What Maxwell's law says? Displacement at point A due to the load at point B is same as the displacement of point B due to the same load acting at point B. Same load acting at point B. The displacements being measured in the direction of the load. The direction of the load. So this is about what? Maxwell's law. Maxwell's law. Here we are talking about displacement. Similarly slope. Similarly moment. Now you take a point A and B. Now you take a point A and B. You apply a moment at point B and find the deflection at point A. Now you apply the moment at point A and find the deflection at B. Both will be same. Both will be same. Apply the load at point B and find the slope at B. That will be same as the deflection at point B due to the load, due to the moment at A.